Welcome to Daily Physics. Today's topic is Newton's law of circular motion.
Let's get physical! Today we're going to show you how significant circular motion is. Circles and circular motion are all around us. They're what keeps this world moving.
In today's lesson, we will learn about circular motion and examples we see in everyday life. So far in physics, we know that an object's velocity is its change in distance over time, and an object's acceleration is its change in velocity over time. We also know that if there's an acceleration, there has to be a net force to cause it. An object moving in a circular motion is always revolving around a central location. Newton's first law says an object continues in its state of rest or uniform motion unless acted on by an external force. So why wouldn't the object continue moving straight instead of in a circle? Newton discovered that the object is being acted on by a force that pulls it towards the center, called the centripetal force.
Centripetal force gives the object an acceleration pointing towards the center of the circle. Knowing Newton's second law, we can state the object's net force is the object's mass times acceleration. To find the value of the object's acceleration, we must first find how fast the object is moving around the circle, or its centripetal velocity. Centripetal velocity is found by dividing the distance the object takes to make one orbit, the circumference to pi r, over how long it took. Now that we know how fast the object is going, we can find the centripetal acceleration. Centripetal acceleration is always pointing towards the center of the circle. To find this, square the centripetal velocity and divide it by the radius.
Looking back at our original force equation, we plug in the acceleration we just found to complete the equation for centripetal force, which is the mass times velocity squared divided by the radius of the path.
Today we're going to use two experiments to describe what circular force is. We'll also go in-depth in centripetal force. First experiment, we're going to be using a hula hoop to describe circular motion. A hula hoop is going to be revolving around this beautiful marble.
As we see, the hula hoop is moving in circular motion. The hula hooper becomes the center of the circle, and by twisting their hips, a torque force is applied and begins its motion. A centripetal force is acting on the hoop, along with its weight and friction from their body. To keep the hoop from falling, the hoop must contain a certain velocity to keep the centripetal force greater than the weight pulling it down. Friction from their body will slow the centripetal force down, causing you to twist your hips more. As you see, the centripetal force is always towards the hula hooper.
For our second experiment, we will show how centripetal force keeps water in a bucket while upside down.
Now that the bucket is filled with water, we're going to demonstrate critical speed. Critical speed is the speed that an object in circular motion has to spin at in order for the object inside of it not to fall out. So if Kayla spins this fast enough, she won't get soaked.
As you heard from our physicist, the bucket must reach a critical velocity while at the top of the rotation to keep from falling. Using our centripetal force equation, we derive the formula for the normal force, N, acting on the water in the bucket. If N is greater than 0, the water will remain in the bucket.
Work it, girl. Work it, girl.
Let me see it, yeah!
Wobble, baby, wobble,